developed the bomb that was dropped in Hiroshima and Nagasaki. My lab was in the plutonium facility. I'm trying to move from this country away from nuclear to so we have the how when they are able to separate carbon 13 monoxide from carbon 12 monoxide. This is a column that is about 80 yards buried at the ground. So you end up, let's say, you have 100 grams of carbon monoxide, then you're able to separate about 1.1 gram of the carbon 13 emission. So normally, carbon, 12, oxygen 16, we're looking at 38, but this one will now be 39 because of the C13. Anyway, so once you have that carbon monoxide, we do a lot of things. From there, we generate methanol. From methanol to acetic acid, bromoacidic acid, cyanoacidic acid, and then we're building up. So it's very, very interesting chemistry. Now, this is isoniazid. This is a first-line drug for treatment of tuberculosis. And I just put it up there to show you the difference between what we call labeled and unlabeled. So I'm going to focus on it's not all right, doesn't matter. So I'm going to focus on this carboxyl function. Okay? Now, because it's a quaternary carbon, there's no hydrogen to it, it has very low pore relaxation and therefore low intensity, in NMR. Okay? So you can see, and I won't bother about any other thing, I will just show you that this one here, that's the carbonyl, because it's downfield. So you look at the intensity of that relative to every other thing. And now we have that carbonyl, carboxyl position now C13 enriched. And you can see how the intensity of that. In fact, this one here at about 140, which is the ipso carbon here, pretty much is barely visible. So with that, you can actually amplify the region that you want to focus on by going in there and doing the specific labeling of that. Okay, so we're interested in these purine-based nucleosides deriving from adenine and guanine, that is adenosine and guanosine. And we're also interested in hydroxymethyl because that gives us a route to the very, very important amino acid, L-histidine, which is found very predominant in reaction centers of proteins. So our project then is to devise a synthesis of adenine and then guanine, and then do an enzymatic ribosylation in order to have a sugar component of that. So isotope labeling chemistry is kind of very expensive and tedious. You can see cost of isotope is always a major factor. And what I've done here is produce in the table dollar amount per mole of acetic acid. So when you're dealing with natural abundance acetic acid, which is not your regular acetic acid that you buy, you're looking at about $23, maybe $24 per mole. And then you can see when we change all the hydrogens to deuterium, you go to 1700. Now, if we have the 2C13, that is the methyl group, they're labeled. It goes to about 18,742. And then if you have the 2 carbons of acetic acid, that's a doubly labeled, then you're looking about almost $34,000 per mole. So it's a very, very expensive undertaking. And therefore, whatever chemistry you're going to develop has to be robust, has to be efficient in terms of the utilization of the isotope and also in terms of the yield. So the chemistry should provide high yield in each step, and it should accomplish isotope incorporation in the minimum number of steps. As much as possible, the carbon deriving from carbon monoxide, if you can use that in your reaction, or as close to it as possible, better, because the more you begin to elaborate, the more expensive it is. And a no-no is to go through a reactant that is symmetrical, because that will lead to isotope scrambling. So these are the constraints. And each of these steps, you have to carry it out on the unlabeled material at least 4 times. You do on a small scale, you scale up, and then you scale up, and you repeat that to make sure that the chemistry you have enunciated is reproducible, because you don't want to go along the line and something bad happens, and then you've just lost a lot of money. You guys can know about Murphy's Law. Do you know Murphy's Law? The students, do you know about Murphy's Law? No, he says anything that can go wrong will go wrong. If there's any chance that it will go wrong, it will go wrong. So you have to mitigate against that. Okay, so we had to, of course, you look at what has been done. And the chemistry that was reported at the time started with this 4,5,6 triaminopyrimidine. And you would either use formic acid, acidic anhydride mixture, or morpholinium formate, or diethoxymethyl acetate. And of all of these, the one that seemed to work with reasonable reproducibility is diethoxymethyl acetate, which from now I refer to as DMA for short. But the synthesis here has the drawbacks that you can see. You're using this in large excess, this is the solvent. If you're carrying out a reaction with label where you're using that as a solvent, is a no-no, or a large excess, you always want to stay close to 1-to-1 stoichiometry. So reagents are used in large excess. And by the way, our major interest is how to close this ring, okay? The annihilation reaction or ring closing reaction. So you look at this chemistry for the unlabeled material, and it looks kind of simple. However, look at what happens if you want to label a specific position in the ring. So let's say we take this C13 here with that amino group. And you see, I don't know if it's particularly immediately obvious that you have 2 ways that ring closure can occur. Between this and this, or between this and this. And if that happens, so you have a situation where this is part of that mesosole ring, whereas in this other case it's outside. So you can't use that. We have to come, and that comes from the symmetry elements there. We have to try to devise a different way of doing that. So in literature, to get around that, they have this diamino 6-chloropyrimidine, again using diethoxymethyl acetate. And you're able to get 6-chloropurine, which in subsequent displacement of the chloride will give you the adenine, and then you can continue your process there. The problem here also is that this diethoxymethyl acetate, as I stated, is in large excess, actually the solvent for that reaction, and very unpredictable. So we can't use it. We have to devise, again, an efficient way. So the challenge then was to devise a common high-yield synthesis route to adenine and guanine. And if you can unify it so that you get to a point where you can branch, which is what we in Atom call convergent synthesis, then that should work. We should have whatever method you develop has to allow access to all the isotopomers. So we need not only the particular isotope, but also the various positions. That synthesis has to be robust enough that anyone that it asks for can be provided. And again, it must be efficient. Our challenge here, a lot of the chemistry has been worked out except for this ring closure. And that was what occupied my effort then. So, and this is what we did. So you have that dichloro the amino dichloropyrimidine. Okay. So, sorry, there's a mistake there. So that's not the name. Then once you treat that with ammonia, and we are using N15 enriched ammonia. So you install that amino function in that position. And then what we did was to take formic acid, sodium formate, actually, C13 sodium formate, which we then reacted with a T-butyl acetyl chloride in order to generate that anhydride. The whole idea is that if you ask, well, you have two carbonyls that can react on both sides of the anhydride, but we deliberately chose that tertiary butyl group to provide bulkiness or steric hindrance in order to channel the reaction to the formyl carbonyl. And we're able to get this N-formyl product. And this was my idea. That's reagent mixture. The first time it's reported in literature. Phosphorus, activated phosphorus, is a well-known oxophilic entity. You can find it in a lot of reactions where phosphorus chemistry is elaborated. And this comes off of a well-documented name reaction called Mitsunobu reaction. We thought we could tamper with that Mitsunobu condition and generate our own condition. And lo and behold, very clean reaction, and we're able to get that 6-fluoro-813C915 and purine, because this position nitrogen and that carbon 13 are enriched. And then once we have that, we do the amination reaction to get the adenine. And then the rest of it is an enzyme reaction that is able to install that deoxyribose unit. So thymidine, potassium dihydrogen phosphate, then thymidine phosphorylase, and nucleoside phosphorylase, which is able to pick up that sugar, cut it off from the thymidine, and be able to transfer it to the purine. Beautiful reaction, clean and very stereospecific in the way it is delivered. So let me just show you some evidence. So this is the C13. You're seeing two C13, one intense and then the other one. But all we're observing is this C13. But mind you that this molecule can exist as a rotamer. So one where the CO is pointing down, another one where it is pointing up. And when it's pointing up, it will be hydrogen bonded to that hydrogen. And therefore, that's why you see two signals there. The other thing we do is we run the N15, tuning the NMR spectrometer. And you see that we again see the double N15 because it can show up in one rotamer or the other. Okay. This is the proton NMR. So here is that proton, but this one here is what you see. It splits by the carbon. So that's why you have this doublet, and then it's interacting with this hydrogen. That's why you have a doublet of a doublet with different J values. Okay? And when we couple that hydrogen, then of course that's what you have. You can see that signal amplified. So we're confident that we made it and that ring closure has occurred. Then we go ahead and do the enzymatic ribosylation, and we can account for all the signals in that proton NMR. Okay? And because we've done the amination, so again, this is the signal. Now the ring is constrained, and we are seeing for the C13 NMR, proton coupled to that split it, nitrogen coupled to that split it into two, and the proton here coupled to that will have that multiplex. So it allows us to do all kinds of NMR experiments. Like I said, heteronuclear, and then multi-dimensional. So you can look, proton N15C13, 3 dimensions, and what have you, be able to pull that apart and extract the information. And also we see 2 N15s corresponding to this and to that. So we're quite confident that we made it. So based on the result that we've seen so far, then we decided to elaborate the whole system. So you have urea, 15N, and then we react that with ethyl cyanoacetate, which of course we can take ethyl bromoacetate and react with potassium cyanide with a phase transfer catalyst, and that's fine. And we get that amino uracil. And then phosphorus trichloride, transform the OH into the chloride, ammonia displaced, stoichiometric amount, and we get that. And then we take bromoaniline and they azotize that with sodium nitrite and we install. So bromoaniline, you can see this one is unlabeled. We use labeled sodium nitrite. That's why I have that red. And then that will do a diazonium coupling to install that to form that azo compound. Under zinc reaction and sonication, that azo bond is broken. Install that amino group there, and then we can do that our formulation reaction. And once we do that, we get our chloro compounds there. And then we do a reductive deamination using isomethylnitrite, dimethylformamide, and heat. And heat, we're able to knock off that amino group C. And now we're able to do our 6-chloropurine. Then we can do our ribosylation. The same thing, now we can carry that forward to here and use the adenosine deaminase in order to convert that amino group to
oxygen.
So, we succeeded in elaborating this. I don't want to bother you with all those, but you can see how we build up that. Okay? So that's one project that we complete. We have it published in Journal of Organic Chemistry. The next project is site-specific labeling of okay? A very, very important
can you hear me?
Amino acid.
Okay.
Some of us have heard about histamine.
Good afternoon.
When histamine builds up,
that's
when you have allergic reaction. Histamine has lost that
the news don't reach you just now.
Biological. Unique amino acid residue in proteins and peptides. Due to that, we need a moiety.
The issue is that
and plays a very, very important role in hydrogen bonding interactions.
that continuous vent. The surge vessel normally has a continuous vent because it's atmospheric. So then
you have the alpha amino function, and then the side chain is linked up to it. So we saw a job as to
at the tip
find
of it.
a way to generate this
every time the tip of that
specifically
used to
label any of those positions,
which we believe that maybe because of
the synthesis
gas that is coming
complicated. They start with this tosyl-methyl-imidazole,
but
lithium.
That little oil now.
It
keeps dripping and
so on. You can see butyllithium. You don't want to
close to that place.
I was a student.
So we are now looking for how do we solve this problem. That line now, only small drain. In fact, before your call came in, I was just about to open the P&I.
That's not a label that you want. You want things that are not that hazardous that can be handled by just any average technician. So it does all of that,
but that drain, the day they tried to open it, the oil will fill that place. Have to close it. So we are looking at maybe we use it as a shutdown item to free that drain because it's the way we look at it. I think
I was asked to take on this project, and like I said, my thing was to make that
section.
imidazole moiety.
So that's what we are now thinking of.
All right.
Of a solution.
I kind of went back and did a literature review. It turns out that this guy, Gordon Shaw, and the co-workers had actually taken ethyl cyanoacetate.
I can't say because I wasn't there when they tried to open
it. And then reacted that with sodium carbonate and
sodium
dithionite, gotten this
which
they then reacted with triethyl to get this
quite a long time. So
and benzylamine provided that entity, and that was very, very exciting because I said we are pretty much home free.
Yeah.
All we have to do is try to knock off this amino group, and then we have our And so that seems to me to be a very quick route to the compound we are looking for. And that's exactly what we did. Ethyl bromoacetate with potassium cyanide gave us ethyl cyanoacetate in 98%. Sodium nitrite in acetic acid, we got that oxime. And then the reduction worked beautifully. We carry it through all the way, all those steps to here. And we are getting about 68% of this. Isoamyl nitrite in tetrahydrofuran under reflux afforded that deamination reaction, and reduction with lithium borohydride gives us our alcohol that we're interested in. Very, very reproducible reactions, none of them requiring anhydrous conditions and all those kinds of things. So we are very happy. Let me just show you, spectra, because you have to see spectra. So for here, we have the ethyl group CH3, CH2, this one, a quartet triplet. And then you see the N15 over there because of that N15 installation. So, well, if you check, so this is that oxime N15 at about 62 parts per million. Okay, and now we have it the other way where there is a ring closure, and you can see now it's at about -118 because now it's part of that ring. And we elaborate this because of the ethyl group, the benzylic CH2, and then you have the NH2, which is integrating to less than 1 because of exchange. Okay, so in that same reaction, we can change it with non-labeled entities, but coming with labeled N15 labeled benzylamine as a way of introducing the other N15 function to the side. I don't want to bother you about this, but you can see the difference. This is now at 200 and negative 213, the N15 NMR. And now we carry that forward, and you can see that this area is looking clean because that amino function is no longer there. And you can go ahead and check the integral. 5 from the ring and then 2 from that. That should add up to 7. So this is 8.4.4. Call that 1.8. So that is 2. And then 3, 4, 5 coming from that. And then you have the 2, arising from the benzylic position. Sorry, this is 2 plus 3 because 2.8 has 3. That's 5. Then 6 and then 7. These things don't integrate to exactly 1 because of issue of relaxation. If we have a long relaxation delay, then we'll be able to come close to 1. So we are confident that we have that. So the next step, of course, is the reduction, which indicate the sodium borohydride, and you have the hydroxy methyl imidazole. Subsequently, you just need to transform this into the halide, maybe thionyl chloride or phosphorus tribromide, or triphenylphosphine, iodine, any of those will give you those halogen derivatives, or you can even make a tussle of that, parachlorine sulfonic chloride to make the tussolate and activate that oxidate nucleophilic displacement. Not a big problem. So basically, then we have that way to go. And then we now want to say, if we have this compound, can we close that ring so that instead of building the purines from the pyrimidine and then adding the imidazole ring, we can start from the imidazole ring and then elaborate the pyrimidine function. And, I kind of stated this, my project time had run out, but this is cyanogen bromide, any of those things will close that ring. And so we can, while making the hydroxy methyl imidazole, get to a point where we can branch off and then get into the purine type chemistry. So in summary, we devised synthesis of labeled hydroxy methyl imidazole. We propose a unification of the synthesis of that purine, and the synthesis allow for labeling of all atomic, that's carbon and nitrogen positions, in all combination of atomic positions and isotopes, employing common reagent as close to the original source as possible. And one important thing here, we have been able to scale every step of that reaction to provide like multi-gram quantities for our purpose. So if it ever needed to be scaled up, we would have been able to do that. Thank you very much for your time. Yeah. Yes,
I'll be aware as voice.
This is something we can actually modify in the lab, and what's under what conditions can we do that?
We just need our basic round bottom flask, and we have to look at what particular imidazole you're looking. All this, we should be very, very durable.
We require
No. I mean, the only thing we require just to confirm what you have made. The chemistry itself is not an issue. So, if you have the authentic sample, you can go and do like TLC. I mean, it's not the best, but you can look at the elution pattern and proceed with that. And also, somewhere so you can look at the functional groups that are present there. If there's a primary amino function, we should be able to see that at about 3,300. If there's a carbonyl, we should see that around 1,700. Reciprocal centimeter. If it disappears, we know it disappears. So it's absolutely doable.
So we can easily modify the structures, right?
Yeah. We show students how to do it. It's not there. It's not a big deal. You can synthesize them. Yeah. Yes, sir.
And can we use that this as a line in metal of a different one?
Well, that's for somebody who is maybe organometallics or whatever. So you know what the binding characteristics are. But those pi and tau nitrogens in the imidazole ring are very powerful because yes, they can. That's what they do in enzyme systems. Yeah, definitely. Yes, sir.
One of those slides, when you
No, there's a geometry of that, molecule.
But it can actually affect its characteristics in its function. Specificity.
Well, at the point where we have that amide, all right? So you have the rotamer, and that's common when you synthesize amides, and you're going to see that. Because if the carbonyl is up, there is a hydrogen bonding interaction between the oxygen and the hydrogen of the nitrogen. Now, if you turn it into a tertiary amide, that goes away. But the good news is what we are doing here is ring closure. By the time we did the annulation reaction with beta-6-chloropurine, it was no longer necessary. The issue of rotamer doesn't arise. And over time, it turns out you can see the one that is the amplified. If you have an equilibrium between them, eventually the reaction will settle it will rotate and close. So it's not a problem for this. If you have the open structure before the ring closure, depending on what you're looking at, you might be seeing more than one signal as a result of that rotamer. And it can be very helpful because now, assuming you're monitoring a proton, you can see that in one case it's very intense, in the other one is not. And you know that that's what you're seeing. And that might help you as you design the experiments for that lab. Okay, good question.
Another question. Performance.
Yes, sir.
So I'm thinking of addressing the case of these new projects to the by inviting the application of microorganisms.
I'm not aware of any, but it might be a possibility. But in this particular case, it will be kind of. I'm not. I know we have the ones that do a esterification reaction. Whatever the bugs do, they do phenomenally well. But I'm not aware of this kind of ring closure reaction that might be enzyme based.
So the usual such thing that we want to microorganisms.
Yeah, I mean it's worth exploring. You have to give it to the microorganisms. Whatever they do exceptionally well. Okay, I don't know if you've looked at the structure of a Taxol, the anti-cancer agent. I mean, look at it. Nobody's been able to really synthesize it. You just bring it up to a point and then derivatize. Nature is the most powerful synthetic chemist that does exquisitely beautiful structures. And we can't even come close. We're trying. Yes, sir.
So, what you know in the synthesis of imidazole,
Yes.
is there any kind of reaction that is going to exclusion at the temperature?
Not really. The only reaction here that is prone to running off is where we made diazonium. The diazonium coupling. There was a point where I said you use a bromoamine and that's why those reactions you have to cool them down to like 0. So what we do is we sit that in ice. Actually, the ice you have to add salt to it. You lower the temperature to like -10, and then you have the sodium nitrite, which you add, dropwise. We don't even isolate that. So in situ you do the reaction. So this is I mean, when I say like we've scaled this thing up without any problem. When you have the solid diazonium source, I know we had an explosion sometime, you touch it with the spatula and it just blows up because it wants to release nitrogen, which is a neutral species, N2. So that reaction is very facilitated. It can be done. So what we do is the floor where you have the anti-static mat to make sure that you don't have static electricity that you're generating. You have anti-static gun. The spatula you use, you have to kind of make sure that all the possible sources of spark are removed. So don't fear, I'm still here, and all my fingers are still intact. Okay.
Do you have any questions from those online? Any questions from the online participants?